Okay, so we're now on part 3 of the Java Executor Completion Service lesson. And what we're going to do here is talk about modifications to the PrimeChecker app to use the Java Executor Completion Service interface and, of course, the underlying mechanisms to make that work. So let's quickly give an overview of this version of the app. The interface is very similar. It allows you to be able to check to see whether numbers are prime, random numbers are prime. And as you'll see, you can do all the stopping and interrupting and rotating and so on cleanly because we're using the Executor Completion Service. Under the hood, it's going to use the Executor Service portion of the Executor Completion Service to create a thread pool with a fixed size number of threads. That's pretty much the same as before. We're going to have this prime callable that's used to be configured with a PrimeChecker, which is a function. And we'll talk about how that gets used here in a second with the FutureTask and the memoizer and so on. And the prime callable allows you to be able to do these two-way calls, which has some nice properties to clean the code up and get the activity out of the callable. And it returns a prime result. Now, we'll look at the code here in a second, but prime result, as I've implemented it now, is what's called an immutable class or an immutable object. And what that means is that once it's initialized, it never changes. And that has some nice properties with respect to visibility, because when you have an immutable object, Java and the virtual machine ensure that that can be propagated cleanly to all threads. It gets published to all threads automatically. The other nice thing, by the way, is that because we're using futures, the operations in the futures also ensure that the data is automatically published correctly. By the way, for those of you who don't come to class very much, please turn your laptops off. They're not to be used in class. I've mentioned that many times. All right, so the next thing is that the main activity creates a memoizer, and the memoizer is what's going to be used to optimize the prime number calls by being able to cache the values. We'll take a look at that in a second. You can see how it gets initialized here. We create a function, but it's actually a memoizer. And we'll look at that code in a second. And that's going to be able to use to transparently optimize the lookups, depending on the circumstances, which we'll talk about more as well. You can see here that we have a stream where we create n, or count, random longs. We map those to prime callables, passing in the memoizer. And then we go ahead and for each of those prime callables, we go ahead and submit the call using a Java method reference. So that's kind of the flow of control. We have a thing called a completion runnable. This is what's used to handle the completions. This is pretty cool, as we'll look at shortly, because it's going to use the completion service capabilities. And we do this by starting a thread and running the completion runnable in a thread. Now, here's an interesting question for you. When I first designed this program, I didn't have the completion handling logic using a separate thread. Instead, what I did is I created a thread pool with 3 threads. My machine at the time had only 2 cores. So I had 2 cores that were used to run the processing. And I created a separate thread that was part of the thread pool. And I went ahead and instead of running a separate thread here, I just went ahead and executed this runnable to run in the thread pool. And my program was really sluggish. In other words, the results didn't show up for a very long time. Does anybody know why that is, and why, if you want the results to be more responsive, you need to create a separate thread here? So what I was doing before is, just to clarify things, this code over here, which creates the thread pool, that was, I was giving it a size of 2, right, because there were 2 cores. And then I would add another 1 to it. So I'd have 3 threads. And my idea was to have 2 threads doing the computations that were computing the primes. And then I would use the 3rd thread to be able to run the runnable, which would then wait for the results. And I found that my program was very non-responsive. It took forever to print the results out. Why would that be happening? Philip? Good insight. You're very close. It's not quite right, but you're definitely on the right track. Yes, Ann.
Because you have only 2 cores and 2 of your
Yeah, great question. So Anne's question, or her observation was, we only have 2 cores, so we're dedicating 2 cores to run the primality check, and then this other poor thing that's waiting doesn't get any chance to run. That's what I thought, but if you think about it more carefully, this solution has the same sort of problem, right? We created a separate thread, and we still have the same issue. Hamid?
It's because of how CompletionService works, and well, instead of writing to queue, so maybe this third queue needs to be done after those 2. The third thread returns after the other 2 are already in the queue.
You're very close. It's not, you're not quite there, but you're very close. Michael?
I guess we have the thread pool set to just the 2 cores, and you have 3 threads when it's cycled between them, but the result displaying will be almost instant, and the CPU bound tasks will take forever.
That's also very close. You're very close. It's hard to, I'll give you the answer because it's hard to figure it out. So what happened here is, remember the way that the thread pool works is you have say, n threads, 3 threads, but then you have a large queue of things to work on, right? So the way it works is if you have more stuff to work on, then you have threads to work on them with. They get queued in a queue, right? That's what how the thread pool works. Wow, sounds like there's a hurricane blowing in here. So what's happening is this code here is getting called before this code here. And so as a result, we're creating lots and lots and lots and lots of callables, and they're getting stuck on this queue. So we're going to have, let's say we have 1,000 prime numbers to check. There will then be roughly initially about 1,000 things on this work queue to be processed. Okay, fine. Then we come over here, and if we go ahead and we do execute, it'll take that thing that's going to get all the results, and it'll stick it at the end of that work queue. So that will never run until all the other items that are ahead of that poor one runnable at the end of the work queue get run. So of course, that thing is not going to start running until you're all the way at the end. And that just has to do with the fact that they're FIFO queues that are used to serve the threads in the thread pool. So by doing this, we create a separate thread that's not queued up waiting for anything, and it will run when it's its turn to run. Because keep in mind that the compute bound, even though the operations are compute bound, the way that the scheduler works in the operating system, it gives every thread a time quantum to run. Let's say it gives it 100 milliseconds or whatever, or 100 microseconds. It's some amount of time, and it gets to run. I think it's 100 milliseconds or so. And so after it runs 100 milliseconds, that thread gets stopped, another thread gets to run. But the problem here wasn't that this guy never got a chance to run. He does get a chance to run periodically. It was that by using the thread pool implementation for everything, there were lots and lots and lots of other callables or runnables ahead of that one in the queue. And so when I first was doing this, like, why is my performance so non-responsive? And I realized, aha, it's because this guy's not getting a chance to run until everybody else is done. So that's why I had to create a separate thread. OK, just I wanted to share that because it befuddled me for a while until I figured out what was happening. Here is the logic that runs in this separate thread, this completion runnable thread. And this is using the ExecutorCompletionService logic. Now, it's not easy with the slide deck to go back and compare and contrast what we did before, but if you recall, what we had before is we had a list of futures, and we would call, for each future in the list of futures, we would say future.get. Remember how I told you, as you guys correctly pointed out, that was going to block, even if other futures were finished computing, that one would not finish. And you could sit there and block. This approach here is different. What we're doing here is we're calling take.get on the ExecutorCompletionService. And take.get, as you recall, just gets the next item off of the completion queue. So this thing will only block if there's nothing finished. But if there's something finished, then this thing will just take it and you'll be able to handle it. So as a result, you don't have this head-of-line blocking problem, which we had with the synchronous future processing model. This is an asynchronous future processing model, where the things are put on the queue only when they're done and we pull them off. The one thing that's a little tricky, though, is you have to know how many things you're waiting for. So we have to know the count. And that's what we're doing here. So we're going to iterate from I equals 0, I less than count, and we're going to get the completion stuff as they finish. Duncan? Take will block until there's something on the queue. But keep in mind that what it's blocking on is the next thing that's done, as opposed to blocking on a specific future, which may or may not be done for a long time, if that makes sense. Ann?
So does this scramble the order of the tasks from how they were submitted?
Yes, and that was also that could also be the issue with the other one, although I guess in some sense you're putting the items onto the future list in the order that you submit them. So yes, you may not get the things back in the same order that you submitted them, but that's okay. You want them back in the order that they complete. Now, for computing prime numbers, it's actually kind of an interesting thing, because if the number is not prime, like if it's divisible by 2, you're going to know really fast that it's not a prime number. If it is a prime number, it takes a longer time to figure that out. So you could certainly have differential times. So what you'll end up with here is you'll end up with the non-prime numbers coming back with their factors very quickly, and then the prime numbers will take a lot longer to run. So you would expect, depending on how you did this, that you would probably have lots of non-prime numbers followed by the prime numbers, because they would take longer to run, depending on how many cores you've got. Okay, so that's the big difference. This call doesn't block synchronously. It can block, but it's not going to block on the future. It's going to block on the queue not having anything in it. Once again, we're able to have our state that we want to maintain across rotations in the retain state class, and we can use get last non-configuration instance and on retain non-configuration instance to move that state back and forth when rotations occur. So here's the prime callable class. This is pretty straightforward. We have this thing called prime result. That's what gets the result back. We have to include both the number we were checking for primality as well as the factor that came back, whether it's prime or not, or its factor if it was not prime. Notice how both fields here are final. That makes this a so-called a mutable object. Once you make an instance of it, it can never change. And that has certain properties that are nice in terms of visibility. Here's the constructor. It just goes ahead and stashes this prime checker in one of the fields. And then the call, this is what's invoked in the context of one of those pools in the executor service. You give it, you create a prime result with the number you're checking, and then we apply the checker, which is a function, which will be memoized, as you'll see in a second, to that number. So that returns a prime result. Not too much different there than what we looked at before. Here's the main activity. So the main activity goes ahead and creates retained state. As you can see here, we've got a lot of retained state. We've got the executor completion service, we have the executor service, we have the completion runnable, and we have a thread. We need all those things to be able to do various operations when rotations occur and to do this in a clean way. Here's the constructor. It makes a thread pool with the number of processors, which in this case is actually 4, because there are 4 cores on my Mac. And then we make a new executor completion service with the executor service as the parameter. Here's the on-retain non-configuration instance. This returns the retained state when you rotate the phone. That gets used up here. When onCreate is called, you figure out if this is the first time in which case it'll be null, in which case you have to make a new retained state object, or if it's a subsequent time in because you've rotated the phone, which means we go ahead and we update the activity in the completion runnable so it'll have this object so it'll know how to get the results printed to the right display. Here is the start-or-stop computations method. This is what gets called back when you click the button. And if it's running, it interrupts it. Otherwise, it starts the computations. Here's start computations. As you can see, what it does is it makes a new memoizer. And then this could actually be a function. We don't have to make this a memoizer. We'll make it a function because that's really what it is. Whoops. Let's go ahead and bring in that class. So we're making this thing called prime memoizer. It's a function, but it's actually a memoizer because the memoizer implements the function interface. We pass in the brute force checker. We could pass a different checker in if we wanted to. Here's where we generate the random numbers, and we map them to be callables with the memoizer passed in, and then we go ahead and submit those all to the executor completion service, so they'll run in the background. We make a new completion runnable with this and the count. We start a thread, we run that. And then down here, you can see the completion runnable. This class stashes away the activity. I should probably make this final, so that's a good idea. Oh, I take it back. I should not make that final. That's not a good idea, because we're going to update it here if rotation occurs. And then here's the code that runs in the background in a thread. This just goes ahead and takes the result. That may block until there's actually a future that's put in the queue. But when it comes back, the get call doesn't block. And we print things out and wrap it up. So that's basically that code. And the only other thing here that's interesting, which we looked at a little bit before, but I'll go through again quickly because it's really cool, is the memoizer itself. So this is the portion of the code that caches the results if they have already been computed. So we use a hash map to get fast performance in a concurrent environment. We have a function, which is going to be what gets called back if we don't have the value cached already. The memoizer constructor stashes that function away. And then here's the apply method. This version here we'll look at doesn't have the timeout facility. We'll add that for the next version. And so what this does is it comes in, it calls get, looks up to see if there's already a value in the cache. If there is not, then the value that's returned is null. We come in that case and we create a new future task passing in the lambda expression that we want to have run when the future task is run. And the thing to note here is, remember, multiple threads could be converging at the same time. And if that happens, then we're going to have a situation where there'll be two future tasks, or n, however many threads come in at the same time, and find there be nothing in the cache yet. We'll have n threads potentially creating new future tasks. However, we only want one of them to call run. Creating a future task is a quick operation. We don't want to have to do the computation multiple times. So once we got ourselves a future task, then one or more of those threads that found that there was nothing in the cache we'll call put if absent. And only one of those threads will succeed, right? Put if absent is an atomic operation, and so it'll stick the future task that wins that race atomically into the cached, into the concurrent hash map under that key. So one and only one thread will succeed in calling put if absent. The thread that succeeds will get back the future task that it just put in, and any other threads that don't succeed in getting their future task put in will get back the future task of the thread that won. So they'll all end up with the same future task, it's just that one of them will have actually put something in there. Now the way you know that is that put if absent returns null if this was the first time in other words, if it succeeded. So if that's the case, if it actually succeeded in getting its future task put in the map, then we're going to go ahead and have that thread, the winner thread, run the future task, which will go off and compute the prime number result for our particular example. Otherwise, the code just falls through, right? It didn't win, but it's got the future task. That future task hasn't been computed yet, so we'll see what that code will do in a second. So this guy goes ahead and runs, does the work, and then all threads, whether it was the one that won the race to put the thing in the concurrent hash map or not, all the threads will come through and call get on the future. And again, keep in mind that if the cache had already been computed earlier, then get will simply return the value right away. You were done. If we were the thread that's doing the computation, by the time run finishes, as you see up there, the result will be done, and get will simply return that result. If we were one of the other threads that got into this portion of the code but didn't get its future task put in, then get will block until the future task that did get put in the concurrent hash map finishes running and computing the value. So this is just a super cool way of being able to do these operations and making them work properly and not calling the function more than one time. All right, if for some reason an exception occurs, then we're going to go ahead and remove the item from the cache and throw an exception. OK, so that's basically the logic. Duncan? Right, so the thing you're talking about is the threads came in, they found there was nothing in the cache, there's n of them, they compete to get to put the thing, if absent, in the concurrent hash map. The ones that didn't win will simply fall through and then block on the future.get call until the other thread that did win is finished running its computation.
And they keep their they're going to go back around and try again?
No. They're just going to block until the other thread finishes, and then they'll get the result. So they're just basically kind of waiting there for the other thread to finish running. When the run call up there finishes, you see where it says FutureTask.run? When the run call finishes, that will then set the state of the future task to a point where a get call on the future task will return. So, because the result has been computed. Yeah, that's a great question. It's subtle code, but it's really cool. Any other questions about that code? Ann?
Can you go back to the stream where you generate parameters?
Yeah. It's back over here. This one?
Yeah. Map to object, does that return a hash map?
Great question. So we'll talk a little bit more later about streams, probably on Monday. But in a nutshell, here's what happens. So new random makes an object. .longs is a stream generating method, and it will generate a stream that contains count random numbers between the range max value minus count and max value. And the reason I do that is I want to generate some duplicates, just because it makes the memoizer more interesting. So this is going to give you back basically longs, right? We get longs back. And then what we want to be able to do is for every long from 0 to count minus 1 in the stream of longs that comes back, we want to map each of those longs, which we're calling here random number, so this is long random number, we want to map that to a new prime callable object. So remember, prime callable is just a class that we're going to use to take a random number and a function, and it'll go off and do its thing in a second. But right now, we're just getting objects. So map to object will take a long, and for every long in the stream, it'll return a new prime callable that corresponds to an object which, when called here in a second by the Executor Completion Service, will generate a result. But these are just objects. So we're converting a stream of longs to a stream of prime callable objects. And then we're taking each of those prime callable objects and we're submitting them one at a time to the Executor Completion Service via the Executor Completion Service submit method. We'll talk more about streams on Monday, but that's what's happening. So it's basically like a data flow model where data is flowing through and it's being transformed by each of these, basically these transformation methods. These are called aggregate operations. This is things like longs is a generator, map to object is an aggregate operation that transforms stuff, and for each is called a terminal operation, and it actually does the computation and finishes up the stream. So that's basically a data flow model. We'll talk more about that shortly. But it's really cool. And the nice thing about this is this code here tells you what to do, but not how it's done. And how it's done is done by the Java infrastructure. And so you'll notice, for example, there's no looping here. And so it's really concise and it's very declarative. It's also, incomprehensibly concise for people who don't yet understand streams. So we'll talk more about that. But it's really cool, and it's the way the world's moving in the way that programming is being done. Most programming these days is moving towards a functional-oriented approach with an object wrapper. And if you look at JavaScript, Java 8, Scala, all these languages are moving in this direction. C++, in fact, is also doing that too. OK, any questions, more questions about the code? It's definitely worth taking some time and looking at this example, because it shows a lot of really cool stuff. So now that we've looked at the code, let's go ahead and evaluate the PrimeChecker app that uses the Executor Completion Service. So this particular implementation fixes a bunch of problems with the previous Executor Service implementation. So one thing it does is it processes the futures as they complete. So rather than blocking in linear order, this will just block until something is done, which is likely to be much more responsive often. And this is a benefit of this asynchronous future processing as opposed to synchronous future processing. The executor service gives you synchronous future processing because it returns synchronous futures that you have to store in a list and then iterate over the list and resolve in order. The executor completion service, in contrast, gives you this asynchronous future processing. Things are processed as once they're done. So it's a little bit more responsive. And then the other thing we do is we use this memoization technique and the memoizer class in order to be able to cache and retrieve results efficiently after they've been computed. And this allows us to be able to transparently optimize the behavior of our prime callable class without having to go in and change prime callable. We just plop in a different function which happens to have a memoizer wrapped around it. Yes, Hamid.
Even using Executor Completion Service, say you have a thread pool size of 2, and 2 of our future tasks that we submitted and are being processed right now are real prime numbers, and we still have non-primes left over, like which are to be run afterward. So in this case, we're gonna block, like we're not gonna get those results first.
Yeah, great question. So the question is, how much magic does the executor completion service really sprinkle over the algorithms in order to make things more responsive? And your observation is absolutely correct. If the input is going to take a long time to run, it's going to take a long time to run. So you're still going to block periodically there. You know, if you knew ahead of time which numbers were prime, you could order your list, but that would sort of defeat the purpose because the whole point is to try to figure out if they're prime. So yeah, you can, if the computations themselves take a long time to run, of course, the thread that's waiting for the results will still have to block. It'll block on take, not get, mind you, but it'll still have to block. So it really is the case, Executor Completion Service gives you a win if you keep the pipeline of completed things, you know, full in steady state, so there's always a result there. But if, obviously, if you don't have computations that lend themselves to that, it's not going to give you a win. It's just that when the results are done, you can get them immediately. Asynchronous future processing gives you that benefit. In contrast, the synchronous future processing that you get with Executor Completion Service, the order in which you ask for the results matters. Whereas here, it's just the results show up when the results show up. But yeah, that's a great observation. There still is a problem. If you use the memoizer for a long period of time for a wide range of inputs, it'll continue to grow and it will never clean itself up. It'll burst at the seams, as it were. And that's because it's not purging the cache, right? The cache is not being purged. It's just growing and growing and growing. We'll fix this problem. Probably won't get to it today. We'll do it first thing on Monday in the next lesson, which covers the Java Scheduled Executor Service. So the Java Scheduled Executor Service allows you to be able to schedule tasks that run at some point in the future. And of course, to give you a preview of coming attractions, what we're going to do is whenever we put an item into the cache, into the memoizer cache, we're also going to schedule a callback to run at some point in the future to take the thing out of the cache. Now, again, you know, this particular implementation will be very simple. It just unilaterally wakes up after an amount of time and says, you know, cache item, you're gone, boom. You can imagine a smarter cache that would keep track of whether or not items had been frequently accessed, and so items that were being frequently accessed would not get timed out right away, right? You'd say, oh, I'll let you live a little bit longer because you're busy, right? You're being used. We'll make a simple solution, but that's just a way to illustrate the scheduled executor service for the next time. Okay, so that's basically the end of that discussion.